Greetings students, I am Eunso Yu from Math MVP. Today I'm going to introduce a mathematical instrument called the Chinese ring puzzle. Our video's contents will be in the order of number 1, what a Chinese ring puzzle is, number 2, the usage of the Chinese ring puzzle, and number 3, the mathematical principles in the Chinese ring puzzle. After watching briefly a short video how to solve a Chinese ring puzzle, number 4 and 5 I'll explain another mathematical puzzle called the Tower of Hanoi, which is also related to sequential equations, and the mathematical principles that apply to the instrument. So first, the Chinese ring puzzle is called the Cardano suspension, Cardano's ring, the devil's needle, or 5 pillars. The Chinese ring puzzle is one of the types of split puzzles that has loops that have to deviate from the ring sequence of interconnected columns. It is said to be designed to soothe the boredom of a single wife when her husband leaves his hometown for combat. As you see in number 4, Oyeonhwan means a Chinese ring puzzle with 5 small rings, and Guyeonhwan means a Chinese ring puzzle with 9 small rings. Like this, the puzzle's name differs according to the number of rings it has. The rules of the Chinese ring puzzle are like the following. Number 1, in any situation, there are only 2 rings that can be moved on an iron rod. Rule number 2, the first ring can be moved from the iron rod at any moment. And number 3, another movable ring is the one immediately behind the one at the front. The usage of the Chinese ring puzzle is like the following. As you can see from this picture, Guyeonhwan's applied version of post and ring fence is a 10-ring ring puzzle and needs cooperation with several people to solve. The photo below shows a type of ring found in the Czech Republic named Czech rings. Mathematical principles behind the Chinese ring puzzle, I'd like to explain the presumptions we made while concluding these puzzle sequential equations. When solving the puzzle according to the 3 rules introduced earlier, you can make an equation based on the minimum number of times you need to move the rings for each number of rings you want to take off. However, you get different equations depending on whether you count moving the first and second ring at once as 1 move or 2 moves. Today we will calculate our moves by counting them as 1 move. If we say the number of rings is n and the minimum number of moves we need to make is an, the calculated numbers go as in the table shown. To convert this data into an equation, because we do not handle equations with a separate pattern for odd number and even number elements in a sequence in our current high school education, we will solve the equation using the 2 equations below. An plus 1 plus an plus 1, which has a pattern of multiplying by 2, and an plus 1 minus 2 times an minus 1/2, which has a pattern of multiplying by minus 1. If we subtract these 2 equations, we can express an in general terms like this. An equals 2 to the power of n minus 1 plus 1/2 times minus 1 to the power of n minus 1 minus 1/2. Next, I would like to introduce the Tower of Hanoi. The Tower of Hanoi is a toy made by Professor Lucas of France. 3 pillars stand on a rectangular plate, and this one pillar is stacked in the shape of a tower with 8 hollowed-out plates in the center. The content of the play is to move these plates to other pillars according to the prescribed rules. To organize, 3 bars are fixed on a plate, and there are n number of discs with slightly different radii and holes in the center, and you need to place the discs in one bar with a small radius on top. The rules of the Tower of Hanoi go like this. Only one disk can be moved at a time. Movement should only be from bar to bar, and you cannot place a large disk over a small. Now I'm going to introduce the mathematical principles behind the Tower of Hanoi. I want you to understand how we can get the equations calculated. So first, let's say that there's only one disk. The only thing you need to do is to move this disk onto another column. So if we call the minimum number of times you need to move an, and n equals the number of disks there are, you can see that a1 equals 1. Next, let's say that there are only 2 disks on top of a column. So because this upper disk is smaller than the lower disk, you need to move this first to another column. And then second, you need to move this to the column you want to put all the rings on. And then third, you need to move the disk right back on. So you can see that A2 equals 3. Next, I'll explain A3. But as you can see, I've circled the 2 rings on top. So because these 2 rings are smaller than the biggest ring, you need to move these 2 first to another column. Let's say C, for instance. And as I've circled here, you can see that that takes 3 moves. This is actually the same as A2 because A2 means the number of moves you need to make if you want to move 2 disks, which is exactly the case here. So this equals 3 moves. And then you need to move the biggest ring to another column because you cannot stay on the same column. So this equals 1 move. And then last, you need to move these 2 disks back on top, which is again A2 moves because you are moving 2 disks, and this equals another 3 moves. So you can see that A3 equals 3 plus 1 plus 3, which equals 7. So if I organize what I just previously explained, it goes like the table below. If n is the number of disks we want to move, and an is the minimum number of moves we need to take, the calculations go as in the table. If we add 1 to an, the pattern is more obvious, and expressed in general terms based on the table above, an equals 2 to the power of n minus 1. Thank you for listening.